The three equations that you need in order to solve any continuum mechanics problem are the equilibrium equations, the kinematic equations, and the constitutive equations. The constitutive equations are the equations that link stress and strain. For example, if you have a hard solid and apply stress on top, you would expect this solid to deform in the direction of the stress applied. But also, you will expect this to deform sideways. The softer the solid, the more it's going to deform. And sometimes you can even have a time-dependent deformation that after some time and keeping the stress constant, the solid continues to deform. How that stress relates to strain depends on the constitutive relationships. And we're going to start our discussion of constitutive equations with the simplest model, which is the model of linear elasticity, and particularly when we go to 3 dimensions, linear isotropic elasticity. Linear elasticity is based on Hooke's law, where a force is proportional to a spring constant and a displacement. So if we see the image for that, it would be this case, and as we said, the force is proportional to the constant spring of the constant of the spring, and also to the displacement. The more you displace, the more force you need to apply. You can convert this to one dimension, and if instead of having a spring, if you have a solid and you divide the force by the transversal area, you can transform this in terms of stress as a function of strain, or in this case, a linear stress as a function of a linear strain, and that's done through the proportionality coefficient, which goes by the name of the Young's modulus. All right, in geomechanics, we're going to have to extend this concept to 3 dimensions. And in order to do that, we're going to have to link the stress tensor with its 6 independent coefficients to the strain tensor, also with its 6 independent coefficients. And our objective is going to find out what is going to look like the property that links those two, the stress tensor and the strain tensor. All right, let's start with some definitions. The Young modulus and the Poisson ratio are just definitions for the elastic properties of a material. If we apply to an element that here could be a cylinder or a prismatic bar, a stress, for example, in direction number 3, as we said before, we would expect the solid to deform or to contract in direction number 3 if we do not let it move at the bottom. The relationship between the strain which is caused during that deformation and the stress is the Young modulus. And you can notice here that because this is stress divided by strain, the Young modulus is going to have the units of stress. For example, pascals, psi, megapascals, or some other pressure or stress units. So the Young modulus again is going to link the change of stress to the change of strain. But now we are dealing with a 3-dimensional solid. And as we were saying before, this solid also very likely is going to expand sideways as you apply this stress in direction 3. And it's going to expand in direction 2, which is what we see here in this planar figure, but it's also going to expand in direction number 1, something that we cannot see in this 2-dimensional figure. And by definition, the Poisson ratio is going to be the ratio between the deformation transversal to the applied stress. In this case, I'm using epsilon 1,1 or the linear stress in direction 1. I could also use epsilon 2,2, but let's stick to epsilon 1,1. And then in this case, it's going to be epsilon 1,1 divided the strain along the application of the stress. And we also put a negative sign here because when we apply, for example, a contraction in direction 3, if this is positive, then most likely we're going to have an expansion in direction 1. And that expansion in geomechanics is going to be negative. So if this strain has a negative sign, then negative times negative, that's going to be positive. Positive divided by positive, that's going to be positive. And therefore, the Poisson ratio is going to be defined for most materials as a positive number. So most materials and rocks are going to have a positive Poisson ratio. There are some weird materials out there that have a negative Poisson ratio, but we're not going to deal with those. So you should expect to see this Poisson ratio to vary between 0 and 0.5. We'll see the differences and the reasons for that in a little bit. All right, so let's see how we measure this Young modulus and Poisson ratio in the laboratory. And here I have one schematic that shows how to do that. Here I have it just in a separate figure. Usually in the laboratory, we take a cylindrical sample, apply to that a stress, and measure the shortening along the direction of the force or stress applied, and the expansion in the direction transversal to the stress applied. The stress is going to be equal to the force divided by the area. The axial strain or strain along the axis is going to be the measured shortening, delta L, divided the original length of the sample. And the radial strain is going to be the change of radius divided the original radius, or what is the same, the change of diameter divided the original diameter. This data, we can plot it, and that is what is usually done when we measure this Young modulus, as it is done here in this plot on the left, where we plot the axial strain on the x-axis, and in general just strain in the x-axis, and stress in the y-axis. This is the conventional way these plots are done. And as the stress increases, then you expect your strain to increase, and usually rocks will exhibit if the red here is the axial strain, will exhibit a period in which there is a stiffening of the rock. This usually happens when the end caps that we're using to apply the stress on the rock, they attach well to the rocks. Also sometimes small fractures are closed during this period, so it's not linear. But then after a while, it's going to linearize, and this is the range in which we measure the Young modulus, and that's usually located before more or less 50% of the maximum value of stress that we can apply on the rock. This test of Young modulus measurement for rocks is usually done together with a failure test, in which we load the rock as much as possible until we see the peak value, which gives us the strength of the rock. So we're not going to talk about that right now, but we're going to concentrate mostly on the elastic part and this region of linearity. All right, so if in this region of linearity, I take the change of stress, axial stress in this case, divided the change of axial strain, I'm going to get the Young modulus. And for the same range of stress, I can also measure in that region the change of radial strain. And notice that the radial strain signature also has some period of adjusting at the beginning, and then it goes through the peak too. But we don't want to measure the Poisson ratio either here or there. We want to measure it in the same range in which we measure the Young modulus. And if we measure that change, the change of radial strain divided the change of axial strain multiplied -1, that's going to give us the Poisson ratio. A plot that you can do in order to measure this Poisson ratio and get it a little bit more easily is by plotting in the y-axis the radial strain, which is going to be negative because it is an expansion, and the axial strain, which is positive because it is a contraction. And if you fit a line to this region, then you're going to find that the slope of that curve or that line is the Poisson ratio. So remember, the Young modulus and the Poisson ratio are just definitions, and they characterize how much the rock deforms, and the Young modulus is a stiffness value. The Poisson ratio characterizes how much it deforms when you apply a deformation in the transversal direction. All right, so you may ask yourself, what are typical values of Young modulus for rock? And we're going to talk later about the Poisson ratio, but let's just stick now to the Young modulus. A soft rock is in general in the order of a 1 gigapascal or less than 0.5 million psi. A hard rock is in the order of 50 gigapascals or in the order of several million psi. And there is no magic number to say what the Young modulus of the rock is going to be, because the Young modulus varies quite a bit. I have here one example. Well, these are all just example values, but you should remember that it's in the order of these numbers. And here I have an example plot that shows the value of elastic modulus for different type of rocks. Something important to highlight that also it depends on the type of rock. Usually igneous rocks are stiffer than sedimentary and metamorphic rocks, unless some type of sedimentary rocks like carbonates that can be quite stiff. And as you can see in this plot, they have the highest stiffness of all this group that was sampled. You can also have very soft carbonates, so not every carbonate is going to be super stiff. In general, mud rocks and porous and unconsolidated sands also, they have a low elastic modulus, but again, you could have a sandstone which is pretty well lithified, and that's going to be very stiff. So if you really want to know what the elastic modulus is, that's something that you have to measure for a particular site. And even in a particular site, the Young modulus can vary as a function of depth. In this example, this is a work of mine with a student in which we were studying the properties at an oil reservoir that was actually subjected for carbon dioxide enhanced oil recovery and sequestration. And in this case, we wanted to study what would be the response of the reservoir when you inject the fluid. And as you can see here, we have a formation in which we have a shale, a sandstone, and a shale. You can see that very clearly from the gamma ray log. We also have measurements of the P-wave velocity or the sonic velocity. This is a property that it's proportional to the stiffness of the rock. And through some equations that we're going to see later on, you can calculate what are the Poisson ratio and dynamic, or in general, just the Young modulus for that rock in the shale part, in the sandstone part, and also in the shale. And you can see that for this particular wellbore, the Young modulus varies more or less from 20 to 50 gigapascals, but it varies with depth. The sandstone in this case is a little bit softer than the adjacent shale. And even within the sandstone, in regions that we have low porosity, the stiffness increases. So if you want to know, again, the properties at the given site, this is something that you have to measure with a combination of laboratory tests and wellbore measurements. I have one more example over here, and let me just come back quickly to the previous one. Young modulus, as shown in this example, is a function of, for example, porosity, but also on the composition of the rock. And here we saw the case for a shale and a sand. But even within the same sequence, you could have, for example, carbonaceous shale, like this one, that depending on the amount of clay and kerogen, when you have high amounts of clay and kerogen, which are usually soft components in a rock, you would expect a low Young modulus. Where you have regions of low clay and kerogen and high content of carbonate, and this is stiff carbonate, you would expect that formation to have a high Young modulus. And we're going to see later on that these variations of mechanical properties are very important for our applications. All right, one more thing I'd like to say about the Young modulus here is that the values of the Young modulus for rocks are generally quite large. So that for typical stresses applied in situ in the order of thousands psi or a few tens of MPAs, the resulting strains are very small, in the order of the percents of less than a percent. That's something that you cannot see with your eyes, and you need usually specific instruments and very detailed instruments in order to measure these strains in the laboratory or in the field. All right, we're going to do one more thing in order to finish this topic, and this is to expand the definition of the Young modulus and the Poisson ratio to 3 dimensions. Let me bring the case that we had over here, in which we have a stress which is applied in direction number 3. So if we have such case, then we can see right straight from our equations over here that epsilon 33 is going to be equal to the stress sigma 33 divided the Young modulus. That comes straight from this equation over here, right? So I move the strain to the left, bring the Young modulus to the right, dividing, and this is what I get. From the second equation, epsilon 11 is equal to epsilon 33 times Poisson ratio with a negative sign, right? So let's put the negative sign, let's put the Poisson ratio, and instead of writing epsilon 33 over here, what I'm going to do is I'm going to use this equation right here. So this is just going to be sigma 33 divided Young modulus. This comes from the third equation. And epsilon 22, as we said in this case, is going to be the same. It's going to be the same value, because it's also transversal to the application of sigma 33. Okay, that would be the set of strains, linear strains in 3 dimensions that I get from the definition of Young modulus and Poisson ratio if I apply a stress in direction sigma 33. But in this case, I'm going to assume that this solid is isotropic. And what that means is that iso means same, and tropos means a shape, and in this case it will be more in the direction of direction, or in the line, or in the meaning of direction. So it means that the properties are the same in all directions. So no matter in this case if I apply a stress in direction 3 or if I apply a stress in direction 1 or 2, the resulting strains are going to be the same. So for example, and let me do it with another color here, if I were to apply a stress in direction number 1 in this case, and now this is, or let me do number 2, it's easier to see in this plot. That would be an application of stresses coming to the sides instead of coming from the top. I would expect a contraction in direction 2. That's why epsilon 2 would be equal to this, and in transversal direction I would expect something similar to what we had before. but now with sigma to 2. And I could do the same in direction 1, and in direction 1, I'm going to get a contraction now in direction 1, and an expansion in the other two directions. Wait, I'm mixing up this, and I don't want to do that. So at the end of the day, by combining stresses in these three directions, 1, 2, and 3, I get to these three equations for which I can use these three independent actions and predict or calculate what are going to be the strains will result as a combination of those. And this is what we have over here. Now summarized in these equations, which are the same that we have here on the right. And I could expand also this to consider the strain, the shear strain relationship with the shear stress. This is through the shear modulus. And you can show that that's related also to the Young modulus and the Poisson ratio. So in fact, it's not that there are three coefficients for linear isotropic elasticity, there are just two, because shear modulus depends on Young modulus and Poisson ratio. And now we have all the equations that we need in order to relate all the three linear strains, epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, to the normal stresses, sigma 1, 1, sigma 2, 2, and sigma 3, 3, and also the equations for relating shear strains and shear stresses. I can go a little bit further and organize these equations into a matrix, and it's going to look like this, where the only thing I did now is just to organize it as a matrix, so that we have here a vector column of strains, a vector column of stresses, and what is in between is what is called the compliance matrix, and depends on the Young modulus and the Poisson ratio. We do this because it's a lot easier to deal with this in computational mechanics, and when we handle stresses and strains at a point, it's a lot easier to use matrices rather than to use 6 equations. And this is also very easy to code. Okay, this equation then goes, it's equation 317, and we said that the matrix that is in between goes by matrix D, and it is called a compliance matrix. However, we can also invert this matrix, and we can express stresses as a function of strains instead of strain as a function of stress. And the only thing I have to do is just to multiply the inverse of this matrix to the left of each term, and as a result, I'm going to obtain what is called the stiffness matrix, where now I have a vector of stresses as a function of a matrix multiplied by this constant. All of this together is the stiffness matrix, and a vector of strains. And with this equation now, if I know the strains, I can calculate stresses. For the previous one, if I know stresses, I can calculate strains. And there is one last version of these equations, which are called the Lamé equations. And I'm going to let you read what it's about. But the only thing that the Lamé equations do is just simplify some of those terms. So the stiffness equation looks a lot easier to look at rather than what we had before. All right, so by doing this, we have accomplished what we wanted. We have related stresses and strains in 3 dimensions through a proportionality value, which in this case it's a matrix, and it is what we were looking in this case. Again, I repeat that when we're using linear isotropic elasticity, this matrix is just going to depend on 2 values, the Young modulus and the Poisson ratio.